as Danny earlier said, and I want to stress this, I'm completely from a different background. I'm an engineer and computer scientist. And I also want to tone down this enthusiasm a little bit. I'm here mainly to present my field, which exists for a little bit only. It's very prototypical. It's a technology basically, and it's represented by a few thousand researchers internationally, but it's still a very much a growing field, and it's still very early on. So I leave it to you whether this could be of interest and of importance to you or not. So yes, I'm Kristof Van Laerhoven. I'm from the Technical University of Darmstadt, and although the pictures show devices, basically the devices are only a small part of our research. They're actually the easiest part because they basically contain electronic components, and us being engineers, we usually don't find any problems in putting them together and making them work. What our main concern and interest is really the machine learning part and the signal processing, and that's what we basically do 95% of the time. So the field is called activity recognition, and what we try to do is try to detect what type of activity a person is doing, either by sensors in the environment, like a camera pointed at a person, or by sensors on the person's wrist or legs, or in the pocket of a person, and then checking or trying to figure out what this person is doing physically. So it's all about physical activities. The top over there has the Wikipedia entrance on activity recognition, which is, I think, quite accurate. And basically that's what we try to do. That's, in a short version, what our goal is. When people publish something in our field about activity recognition, applications are usually not really the concern. We have had a lot of papers that presented this as a possibility for elderly care, for the detection of activities of daily living. Was very popular, and where there's lots of funding is fitness and well-being, apart from, of course, defense projects. Psychiatry has not been covered at all, so I've put that there in the middle, but basically there's no applications where this has been suggested, but it might be, for instance, as Yanni suggests, for bipolar patients, they're helpful. What has been done a lot is workflow monitoring, where people want to, for instance, check engineers whether they go through the steps properly and automatically display information from user manuals. That's where a lot of companies have interest in this type of research. And early on there has been lots of interest in groupware, so ICQ, Skype type of programs that detect what the activities that the person is doing and then displaying it as a status, for instance. And memory support is something relatively novel that Microsoft is doing at the moment within our field. So it's basically just a quick check on applications, but as I said, usually it's also not really a concern for us. What we are interested in is basically this signal processing. So we look at signals from the wearable sensors in our case and try to detect what these small patterns are. And usually they are gestures. So imagine it as you wearing a watch, that watch containing some extra sensors. In our case, we use accelerometers mostly, and those sensors pick up the motions that the person are doing, and also the posture of the wrist, for instance. Most of the time, we use wrist-worn sensors. As you can see, for different activities, you get different motion patterns, and the detection of motion patterns is the first step, basically, that we try to do. And the second step is basically linking those motion patterns as an accumulation of evidence towards activities, the real physical activities that tend to happen. So that's basically what we try to do, in a nutshell. The hardware design is something we have to do because there's basically no hardware available, or there's no devices available that we can just buy and use. So we build them from scratch. They have been evolving over the last years. I've been in this field for about 10 years. Over here you see on the left side version 4, and on the right side version 5 of my own device. It is in essence really a microcontroller driven device that senses sensor data, processes it, and puts it on a piece of memory inside this watch. You can then charge batteries and upload data via a USB cable, and it holds enough information for, say, a couple of months. The main problem is usually the battery. The battery only lasts at the moment for about a month and a half. So the casing is, as you saw in the previous slide, pretty important. there we are very novice, and we just do the best to make it all fit and make it work reliable. In terms of electronic design, the components are getting smaller, so that's actually in our favor. And also components are getting integrated with each other, so the whole thing becomes smaller almost automatically by just us waiting and seeing how smaller and smaller the sensors are getting, and also how much more accurate and how much reliable they will get. So again, left is about 2 years ago, right is a year ago. Just as Daniel's project, basically our project is also open source. Of course, with hardware this is a little bit trickier, but all our designs are also freely available. And about a dozen labs worldwide have now borrowed our design and made their own devices. Which, by the way, as Yanni mentioned, are very cheap. So basically the component cost is about 30 euros, 20 pounds, but of course the effort in making them is still depending on what type of lab you have, what type of application equipment. Right, so as I said, most of our goals are software-wise, to detect certain things and to model certain things. Part of the things we are busy with is basically getting and acquiring all the sensor data together. For instance, from multiple body positions, this is pretty tricky. So in this case we have, for instance, 3 sensors that a person is wearing for training exercises, and to afterwards synchronize this data is not as easy as you might think. In this case, this is data from somebody doing a martial arts exercise, and as you can see from the bottom plot, these are the legs are basically doing a certain type of kick, and trying to figure out what type of exercise and even what type of expertise this person has is one of the things we try to establish with our algorithms. One of the main things one of the main interests of myself is really long-term doing this. So not just for a few hours, as there's many applications that just require the patient, or sorry, the user to wear these sensors for just a little bit, but really for doing this non-stop over several weeks or months even. And there the problem becomes really how to model all of this data, and also programming, basically generating the algorithms to browse through all this data. So how do you effectively represent this data, how do you zoom into this data and zoom out in this data if you want to evaluate it, which we usually as people programming these algorithms or developing these algorithms really want. And as you saw in previous slides, basically our data is pretty high resolution, not only in what they give us as values, but also in terms of how much data they generate per second. It's usually about 250 samples per second per axis. So for a 3D accelerometer, one single one, you generate quite a bit of data. To accurately model that, it's again a challenge for us. And to do this over a long period of time, so here you see, for instance, part of a 3-month data set. You can see in the middle more or less the nights, and the rest you can see the days. So here you can see, for instance, if you're familiar with actigraphs, the link. But unlike actigraphs, which just monitor the intensity of activity, we basically try to recognize what type of activity you're doing. And the data, therefore, is also a lot more fine-grained and has a lot more resolution.